In the last video, we introduced the notion of a fixed point. And fixed points are important because if the system approaches some limit, then that limit must be a fixed point. In other words, if an approaches some number L, then, well, L is a fixed point. Okay, and I'll remind you that a fixed point satisfies L equals G of L, or we also called it A star in the previous video, and so we could easily reword that, write that as if A approaches A star, then A star is a fixed point, which means it satisfies this relationship. Okay, so that's the reason why we're so interested in this, that it can tell us something about where a system is going to end up in the long run. But what do you do if there are multiple fixed points? If there are multiple fixed points, it's not necessarily clear where the system is going to end up. And actually, even if you just have a single fixed point, there are no guarantees that the system is going to approach the fixed point. This just says that if it approaches something, then there must be a fixed point. But it could be that the system just goes off to infinity. So in a previous example, we looked at this difference equation, an plus 1 equals an plus r times an times 1 minus an over q, the logistic equation. And so to illustrate what goes on there, I'm going to show you a simulation in just a moment, but I'll remind you that the fixed points we found were 0 and q. And so there's sort of two candidates for what the system could approach. Let's look at a numerical solution now and see what actually happens. All right, so I've set up the model. I've got a function describing my change, consistent with what we showed in the previous slide. And I've set the capacity of the environment to 10, and the growth rate, R, is 0.25. And I'm going to start with an initial value very close to 0, which, if you recall, was the first of the two fixed points. And we're going to then simulate this for 50 steps and see what happens. All right, so we've simulated it, and notice we started very close to 0, very close to a fixed point. But what happened was the solution slowly grew, and then it picked up steam, and then it approached 10, which was the other fixed point. So interesting, we had two fixed points, but in this case, it sort of moved away from 0 and moved toward Q. If I change the parameters around just a little bit, though, say I change R and make it negative, you'll see in this case, it looks like it stays very close to 0 and in fact approaches 0. And even if I start really close to the other fixed point, I'm going to still end up close to 0 in the long run. So what that means is there's something fundamental about how these parameters affect these fixed points. And in this case, we would say that the one that the system approaches over time is called stable. And the one that the system does not approach over time, that it moves away from, is called unstable. And so what we're going to try to do in this video is understand how we can actually determine whether a fixed point is stable, and in doing so, determine whether it's something that we think the system is going to approach if you go nearby. All right, so let's return to the slides here. All right, so we want to know which equilibrium values or fixed points are stable, and we'll start with the definition. We're going to call an equilibrium value of a dynamical system stable, or asymptotically stable is the technical term, if there is some neighborhood absolute value of A minus A star less than epsilon, such that for initial conditions in that neighborhood, AN approaches A star. In other words, let's put this in layman's terms. This is saying that if A0 is sufficiently close to A star, then AN will approach A star. All right, so if it's stable, then as long as we start pretty close to a fixed point, we're going to end up approaching it in the long run. Now, this is a little bit of a very technical definition. It doesn't give us a lot of information about how we actually check to see if something is stable. In fact, trying to apply this definition directly can be a bit of a challenge. But we'll learn a theorem in just a moment that can actually help us do this a little bit more easily. All right, so here's the theorem. It says that if A star is an equilibrium value of a dynamical system and G prime of A star is less than 1, then A star is asymptotically stable. So ultimately, if we have this function on the right-hand side, g, and we can take the derivative of that and plug in a star. If that quantity is between -1 and 1, then we conclude that it's stable. And notice for our linear equations, which we already know that they're going to approach, we said an plus 1 equals ran plus b, has the fixed point b over 1 minus r for absolute value of r less than 1. We can show that that's consistent with this because notice, if you were to compute g of a, would just be r times a plus b. That's the right-hand side of our equation. And g prime of a is therefore just r. And so the condition this theorem tells us is that the absolute value of g prime of a, which is the absolute value of r, must be less than 1. Exactly what we argued using a completely different approach, using an analytical solution in a previous video. All right, so this condition does match up with what we know about linear systems, but we can also apply it to nonlinear systems. And to understand why this works for nonlinear systems, we're going to outline the basics of a proof. All right, and so suppose that an plus 1 is equal to g of an. And what we're going to do now is we're going to assume that we start, we'll define a new variable, an equals epsilon n plus a star, where this epsilon is going to represent our distance from the fixed point. So if epsilon is 0, then an is equal to a star. We're exactly at the fixed point. If epsilon is positive, then we're above the fixed point. And if it's negative, we're below the fixed point. Okay? So what I'd like to do is write down a difference equation for epsilon. All right? And so we could write down a difference equation as follows. On the left-hand side, we had an plus 1. And so we could say this is epsilon n plus 1 plus a star. And that has got to be equal to g of epsilon n plus a star. And now let's suppose that epsilon is small. So it's close to 0, but it's not exactly 0. If that is the case, then we can approximate this function on the right-hand side using a Taylor series. Or more precisely, we're going to just use a linear approximation. And so this term on the right-hand side can be written as approximately g of a star plus the derivative at a star times the difference between the current state and a star, which is just epsilon n. And notice, when we write it out this way, there's some simplifications that we can make. If a star is a fixed point, then that is just a star. And so we can say that epsilon n plus 1 is approximately, well, if we subtract off a star from both sides, we'll be left with g prime of a star times epsilon n. And g prime of a star does not depend on epsilon or n. It's constant. And so this we can think of as just some number. Let's call it r. And so the new value of epsilon is equal to the old value times this constant r. And so that's the type of linear difference equation we've studied thus far. It has a nice analytical solution. Epsilon n is going to be equal to r to the n times epsilon 0. And so we can now say exactly what's going to happen if the absolute value of r is less than 1. Then r to the n goes to 0, which means epsilon to the n goes to 0. And if epsilon to the n goes to 0, then an must go to a star, since epsilon was the difference between them. All right? So the idea is if you start close to a fixed point, you can think about this as behaving like a linear system, where the derivative of that function g is the constant r. And then we can apply our knowledge about linear systems to the nonlinear system to predict the behavior. And similarly, if r is greater than 1, you would see that this would grow over time and we would move away from the fixed point. Now, this proof is not entirely rigorous. We've actually omitted some other stuff from this Taylor series, but gives you the gist of the argument at the very least, and this can be made more precise by using a theorem called the mean value theorem. All right, so point of this is to recognize that it is the derivative of g that tells us whether we have a stable fixed point or not. All right, and we can extend some of our definitions just a little bit further. If a star is an equilibrium value of a dynamical system and the derivative is greater than 1, then we'll say that a star is unstable, and that means that if you start close to the fixed point, you will move away. And if g prime of a star equals 1, then a star may be stable, unstable, or it may be what's called neutrally stable, which means you don't really move away, you don't really move toward it either. You stay pretty much the same distance away. All right, let's see if we can apply these theorems to our example of the logistic equation. All right, so which of the fixed points of the dynamical system are stable? Well, recall we had two fixed points. We had a star equals 0 and a star equals q. See if I can write a q. All right, that looks a little better. All right, so that's our two fixed points. And so let's start with a star equals 0. An plus 1 is equal to g of an, which is an plus r times an times 1 minus an over q. So the right-hand side is that whole expression. And let's take a derivative of that. And I'm going to leave off the subscripts just for simplicity's sake. See, the derivative of this would be, derivative of an would just be 1 plus, now if I look at the expression above, I have an r times a times 1. Its derivative is just going to be r. Minus, I'm going to have an an squared times r over q if I FOIL that out. And so its derivative will be 2ra over q. All right, so there's my derivative. And now if I look at this first fixed point, a star equals 0, and I compute g prime of a star. So that's just g prime of 0. I get 1 plus r. And we want to know when is that stable, and it's stable when the derivative is less than 1. So here we plugged in 0 for a, and so we can try to rearrange that equation just a little bit. We have 1 plus r. That must be either less than 1, or not either, it must be less than 1 and greater than negative 1. Or we could say that r therefore must be, if we subtract 1 from everywhere, we'll have minus 2 less than or equal to r less than or equal to 0. Okay, so if r is between negative 2 and 0, then it must be stable. And if we look at the other fixed point, plug that into our derivative, absolute value of g prime of a star when a star equals q would give us 1 plus r minus, if I plug into q for a, I'm going to have a 2r times q over q, so minus 2r. So my derivative ends up being the absolute value of 1 minus r. And so we need the 1 minus r to be between negative 1 and 1. And we can rearrange that just a bit. 1 minus r less than or equal to 1, we could write that as r is greater than or equal to 0. And then if we do the other side, so that's taking that part and rearranging it just a little bit. And if we do the other part, we could bring the r over to the other side, and we would have r is less than or equal to 2. Okay? And so when we put those all together, if r is between 0 and 2, then we can conclude that we have a stable fixed point of Q. All right, so those are our predictions. Let's go back to our numerical solution and check to see if that's reasonable. All right, so we'll start with an R value that's positive, and I'm going to start our initial value right in the middle to see which one it's going to approach. And so we'll start, A0 is just going to be Q over 2. And so if R is 0.25, that's definitely between 0 and 2, and our analysis before suggested that means that Q is the stable fixed point. And we see that indeed it does seem to approach the value of Q, which was 10 here. On the other hand, if we make R negative, then the claim was that 0 is the stable one, and our numerical solution bears that out as well. We approach 0 in the long run. All right, let's see what happens if we make R bigger. So we said only between 0 and 2 is it stable. So what happens if we make it 2 1/4? And we're going to need to change our axes just a little bit. So let me comment that out. Interesting. So at this point, it looks like we started at 5, and we started bouncing around, and it looks like we go above 10 and below 10, above 10 and below 10, and just keep bouncing back and forth between those two values. So when R is bigger than 2, neither of the fixed points are stable. That means we don't approach either of them. And in that case, you can have some more interesting behavior. This is what's called a periodic orbit. We're oscillating between two different states, but we're not approaching anything in particular. And if we keep increasing R, you can get all kinds of interesting behavior. So I'm going to make it 4.25. And doesn't seem to like that. It says we're getting really, really big numbers, so that's not good. So we'll stop that. Let's see if we make it, how about 3.45? Same thing. So it seems like when we choose R to be too big, you can actually go off to infinity, and that's a bit of a problem. And if we try R values on the other end, like negative 2.1, we'll see that we also get some interesting behavior. So again, there's more oscillation here. And all right, let's try something a little bigger, 2.5. So that's interesting. Now it's oscillating between values, but it seems like it has 4 different values it's hitting. There's 1, 2, 3, and 4. And if we increase that further, we're going to see that even stranger things happen. And at some point, you can actually show this will devolve into what's known as chaos, meaning there is no regular repeating pattern. It just oscillates what appears to be randomly. It's not random, but irregularly, indefinitely. Okay? So approaching a fixed point is one possible behavior. If you have a stable fixed point, then you're most likely going to approach that in the long run, or at least if you start sufficiently close, you will. But if you don't have stable fixed points, there are some other interesting things that can happen. You can oscillate forever, or you can even devolve into this irregular pattern of behavior known as chaos.